Okay, hello everyone. Okay, so I'm going to talk about type theory and implicit computational complexity, not in that order, but I thought it sounded better that way. Can everyone hear me?
Your mic is not turned on.
Can everyone hear me now?
Yes.
Yes, excellent. I will just move things so I'm not standing in the way of the. I've just realized the complexity of this, that I'm remarkable to this, then wireless, backed via Zoom onto the screen. Okay, so hopefully nothing will go wrong. Okay, so the point of this is, first I'm going to introduce implicit computational complexity, and then work out how to combine it with dependent type theory, and to hopefully give you sort of quite a powerful system. So first, what is implicit computational complexity? So implicit computational complexity is the idea that we want to capture complexity classes like P or NP, so polynomial time or non-deterministic polynomial time, via some kind of programming language. So we want to, in essence, make a programming language which is only expressive enough to write things which are in some complexity class. So that means when we run it, then the time taken to execute the programs in this language are within this complexity class. So already this is a slightly fuzzy concept, just as I've stated it, because as everyone who's ever argued on the internet about programming language knows, you have to separate programming languages from their implementation. So you can't say Python is an interpreted language because someone somewhere will say, well, you could have compiled it, couldn't you? So I'm going to have to give with this, this is a language such that it is possible to make an implementation that always runs within that complexity class, because you could always give a really bad implementation which didn't. And what I'm going to show you is how to make a programming language, or several different programming languages, which soundly and completely capture functions which are expressible in polynomial time. So it's not going to be complete in that every polynomial time program can be written in the language. It's going to be complete in that every function which is computable in polynomial time is expressible in the language. I'll get to what I mean by that. I also want to sort of separate this from descriptive complexity, which is another way of connecting logic and complexity. So descriptive complexity is where fragments of logic, so you might say existential second order logic or something, the satisfiability problem for those captures over finite models captures a particular complexity class. So second order existential logic captures NP, for instance, over finite models. So that's not what we're doing here. We're doing a very kind of program-based thing, programs that you can write within the implicit computational system, computational complexity system, run within a certain complexity class. And also the implicit part is important. We're going to try and do our best never to talk about the sizes of things or the number of steps a program is going to take. So there are type systems for complexity where you actually annotate everything with how big it is. And then you have an effect system which tells you how many steps you're taking. And then you turn programming into an awful, tedious bunch of combinatorics about how many steps it exactly takes to iterate through something. And it's horrible. What we're going to do here is try and make type systems where you never talk about the sizes of things. You just, by the act of writing a program within a slightly restricted system, will make sure that we stay within a certain time bound. And the cost of that is that we won't know many details about what the time bound is. So it's just going to be polynomial. We won't even know the degree very easily. Okay, so let's see. Right, so I'm just going to give a quick lecture plan. So today, which is Tuesday, oops, this will be a thicker pen. I don't want that to be red. Sorry. Right, I'm going to cover linear types and P time, Wednesday, soundness via realizability. Thursday, linear dependent types. And Friday, combining Tuesday and Thursday, well, quantitative type theory plus implicit computational complexity. So it's basically putting together Tuesday and Thursday to show how we can use dependent types plus a characterization of p-time to define other complexity theoretic notions like NP or coNP and some probabilistic classes as well.
Are you planning on getting shantier through the week?
Am I not loud enough? Oh, getting bigger. Oh, right. Yes. Yeah. Yeah. Okay. As I write faster, I make more capitals. Okay. So, and yeah, if you have any other questions, please shout out. Oh, yes. That's the whole reason for being here. Oh, this is like everything should be this high. Okay, so I'm going to start with the linearly typed lambda calculus. So why am I doing this? So I'm going to try and use a linear type system as to start out from a kind of computationally impoverished base. We can start to then build up to have the complexity levels we need. So if we started with just a lambda calculus, then already the problem of normalizing lambda terms is extremely high. I didn't actually know this, and I tried to look it up earlier this week, and I could only find a paper which was inaccessible to our library by Helmut Schlichtenberg. But I think from that, it's somewhere very high up in like exponential, there's some hierarchy of primitive recursive functions, and it's at level 4. But it's a very, very long way from being any kind of polynomial. But we can start with the linear lambda calculus. I'm guessing that not everyone here has seen the typing rules for a linear lambda calculus and how they work. So I'm going to go through it. So we've seen now several ways of seeing the simply typed lambda calculus. But the point with the linear lambda calculus is we have precise control of how the variables are used. And what this means is that we just sort of do it by controlling the context. So the traditional way of doing the simply typed lambda calculus is we start off with some types. So we're going to have A and B types, and then we'll have a unit type, which I write as I. We'll have the tensor pair type, which I write as A tensor B. So it's not a coincidence. This is the same notation as the symmetric monoidal categories in Chris's talk. And then we'll have function types, which are A lollipop B. So these are the linear functions. These are functions that use their argument once. And we'll have some base types. So it's little a. Okay. Now, how do the typing rules look? Well, we have a variable rule. Which says that if we have an A in the context called X, then we can use it. But crucially, we have nothing else in the context. So there's no kind of idea that we have too much and we're just picking out the thing we need. We just have the A. Then we have function construction. So this looks very similar to the traditional scheme. So the only difference here is that I'm writing a lollipop instead of an arrow. Again, if we can construct a term which has a free variable X of type A, gives us a B, then we can lambda abstract over the X to give us the functions from A to B. Now, key difference comes in this rule, which is the application. So here, we've constructed an M using the resources in gamma. And that's the function we're going to apply. And we've constructed an N using the resources in delta. And then, in the conclusion, we put together the gamma and the delta, but we don't assume that there's anything shared between them. So the resources, or variables, if you like, so variables here are standing in for resources, used by M and used by N are separate. We're not allowed to share anything between them. So this is what makes it linear, right? So if we wanted to use, what we can't do is use the same variable in M and N. So this is the linearity. We're not allowed to duplicate variables. Yep.
Do I need the, I mean, because we care about complexity only,
Yep.
do we need to have in the variable rule, right? We can throw away stuff, right? Because
Yes,
we care about.
that's true. Yes, I'm going to come back to that. Yeah. So the question was, in the variable, if you only care about complexity, we can throw away stuff because we can sort of consume more money, fuel, whatever, than we actually need, and just throw it away if we don't need it. So that variant is called the affine linear lambda calculus, and in that one, we are allowed to have extra resources in the variable rule that is are thrown away. So this is affine. Okay, so that's the introduction elimination rule for linear functions. Then where it gets a little bit different is for the products, the tensor. So the introduction rule looks like this. So again, we need separate resources for the two halves. So again, we're not allowed to share the same gamma between the two halves here. So in simply typed lambda calculus for a product rule, this is gamma and gamma. And then we've got a single gamma at the bottom. So here we've got separate resources for the two halves. Two halves of the product give us two separate parts here. But then when we eliminate them, we cannot have projections as we would have in a simply typed lambda calculus. So we can't take first and second because that would mean throwing resources away. So even though that's allowed here, in general, that would mean throwing resources away. So what we have instead is a let construct. So we have a term of type A tensor B. And I'll do it vertically. Some other term which depends on having an A and a B gives us back a C. Then all together, we decompose with a let and get our C, right? So intuitively, we take our M, we run that somehow, that produces a pair of X and Y, and they go into the N, which produces the C at the end. So we're decomposing the pairs, producing the C at the end. And then finally, we have the rules for the unit. So this is, in the full linear system, we might just have, we can make a unit value, but not only do we not need anything to make a unit value, we're not allowed to use anything to make a unit value. Unless it's affine, in which case we might have a gamma here. And then also we have to explicitly eliminate our units in this case. We have to have a rule which says if I have something of type I, and then something else, C. Right, so this is sort of saying M is, we know it's a star, but we have to actually dispose of it as we see fit. So if we had something which was some kind of discard thing, which could discard the stuff in gamma, then this would say explicitly we're going to discard or drop kind of Rust terminology. Okay, so that's the traditional presentation of the linear lambda calculus. It's quite a extremely restricted system. Yep.
So the left hand you have like that you introduce that because we can't have production like a projection in the traditional way,
Yeah.
right? So I mean, this is a stupid question probably. Like let's say you have a tensor product term that contains a m term and like a term A of type term m of type A and n of type B.
Mhm.
So and I use the resources gamma and delta for making that.
Yeah.
So what prevents me from getting the term m in a context with gamma and delta? Like I could directly do that, right?
This term m.
Yeah. So what I'm saying is that, so let's say I have that.
Yeah.
Then why can't I derive delta, so gamma delta m of A? Like,
Oh, right. So in without the affine addition,
yeah.
then you just won't be able to do that. So it will not be admissible. I guess what you're asking is if I have a derivation of this, then how could I sort of transform that into a derivation of this for any arbitrary delta? Is that what you're asking? This one.
Yeah, I was more like, let's say you said gamma comma delta
Yeah.
derives m n.
This
Yeah,
product.
that let's say I derive that.
Yeah.
So I already know that using both of those resources, I constructed
Yeah.
that. So why can't I just derive gamma, delta, and m or n, just like the normal production, projections?
So because there's no rule for projections.
Okay,
So if you try and do it with the let, you won't be able to, because you have to use both of these.
yeah. So I mean, is there any reason? Like, I mean, is there anything that will go wrong if I use it that way? Like, I mean,
Yes,
why
but-
it has to be this way? That was my
Right. So the whole point is that we want to make sure that if something's in the context,
Yeah.
then it's used at most once. And this will be the semantic property that we need. Because what's going to happen is that the things in the context are going to represent the fuel that makes our computation go.
Okay.
If you're allowed to use it more than once,
Ah.
then you can duplicate it and use that to generate more and more
Okay. Okay.
fuel to make
Okay.
it go.
Okay.
Right.
That's a philosophy in which.
Yes, this is so the whole point is that the things in the context are precious resources. Well, they're not just precious; they're also kind of immovable. We cannot duplicate them freely. Yeah, and in tomorrow I'll talk about the semantic model that actually gives some teeth to that statement. Yes, the whole point here is that we cannot duplicate what's in here. If we can, then we break the system. Okay. So I want to say there is a bug in this system as written, even though this is what you'll typically see in a paper for linear type systems. Then I want to say, like, if you read it literally as written there.
You need the context or invariant of the permutation.
Yeah, right. So I've written gamma comma delta. Really, this is a funny comma, which also does a bit of swizzling as needed for the term, right? So it doesn't. There are systems where the order matters in the context, but this one doesn't. So this when I write gamma comma delta, it means that there is some permutation of the context which contains all of these things once. And the fact that that's like that actually makes this system sort of tricky to deal with in a formal sense. If you try and formalize this in a theorem prover, you get into horrible problems with permutations here, because the permutations end up between every rule. We go, oh no, maybe we could have permuted a bit. And if you try to do other things like add other features to the language, it gets horrible. So one way around this is to annotate the variables with how they're being used, which is a slightly more subtle but useful way of doing it. So this is sometimes called quantitative type systems. And I guess the most expansive version of this is the granule system of Dominic Orchard and collaborators. And what we're going to do here is, instead of just having the variables being in the context or not, we're going to have variables in the context and annotate them with elements which show us how they're being used. And the way they're going to do this is to use a semi-ring, or in fact, just a monoid for now. So again, we're going to have the same types. Base types. But now contexts are going to be constructed from the empty context, and the context extended with a new variable and some annotation that tells us how that variable is being used. So for now, let's just let these annotations be natural numbers to say how many times that one's being used. And that means that we can define an addition on contexts, which is pointwise. So in particular, context has to be the same length. So E plus epsilon is epsilon. We have the same variable, but we add the usages. Yep. Okay, so we're adding empty context. We get the empty context. We're adding context that have the same variable, same type, different usages, and we just add up the usages here. Now we can write out the typing rules, and these get kind of interesting because we can say that in the variable rule, everything else is zeroed. So I'm using this notation to mean everything in here is like multiplied by 0, or the usages. And this one is being used. So if you think this is a bit like up to permutation, a basis vector, right? There's one particular one in it.
You have some other zeros after, right?
Well, okay, so I said up to permutation, but yeah. Yes, yes, okay, yeah, fair enough. Just also being lazy. Yeah, okay. So we've got everything 0 except the one that we're actually using. Then the function rule is pretty much the same. So it's a linear function, so we're using it once. And now, in this one, we add up the usages. Right, so before I had this comma, which really meant that the two sides were like a distinct sets of variables, and they were being put together and then swizzled up a bit by permutation. Here, just as you would do in the simply typed lambda calculus, we would have two collections of identical sets of variables. So this should be the same thing, except now we add up pointwise the usages in each one. So if we use an x in here and an x in here, then we add it up and say it's used twice in here. I'll leave as an exercise to do the tensor and I rules.
There's a question?
Yep.
Sorry, just to clarify, have you got around the issue of permutations? Or
Yes.
you,
Yeah, so here, so we fix an ordering is this the same way which is kind of was implicitly done in Connor's presentation, right? That you're only ever adding to the right. And so when you get to the leaves of the tree, they're in a certain order. So at no point do we ever have to permute the context. And then afterwards, if you like, you can prove that it's admissible to reorder the context. I think.
And so here in the lambda rule, you're assuming that this X is somehow fresh and doesn't appear in the context, or
Yes. Oh yeah.
okay. Because you're not adding it with the plus, right? You're just putting the X.
Oh yeah. So this comma is now this extension thing, and yeah, implicitly I'm saying this X doesn't appear in the in gamma.
Sorry, one more question, but maybe we come to this. Is there any meaning of having now a real number or something? Why semi-ring? Why not just integer? I mean, or
Oh yeah. So I should say. So I said we're going to use integers here because all integers count usages, but there are other semi-rings one could choose. So some people, or Dan Gika and his students, have used real numbers to interpret them as delays. Like this is how long this, like they're making circuits. So you can think of these things as circuits, and how long will it take until this one is ready? You can also use it to say how sensitive this term is to this variable. And then this is some kind of inflation in the metric space sense. So by default, you're kind of one sensitive, but you can scale this and say that I'm sensitive to some parameter in variation in this argument. Other ones are you can do security analysis with this by making this a lattice of principles. And then information can only flow from it if this is less than the private one or greater than the private one. Something. Right, so there's lots of different semi-rings you can choose. I'm just going to choose natural numbers for this. But what I want to get on to is the nice thing we can add now, which is modalities, where if we have M has type A, then if we have any arbitrary row, we can sort of multiply this M by the row. So this is something which is now going to be usable for row many usages. So, but to do that, we have to say that the context is available for that many usages as well. So again, we can see there's kind of linear algebra going on here. We have the basis ones, we have addition, and now we have scaling. And again, there's an elimination rule for this. And now this one is annotated with row. Right, so what's going on here, if we've got a thing that we can use row many times of A, then we can indeed use it row many times in N to produce a B, and then that lets us put it all together. We have to combine the other resources that were used in M and N.
We have to add something. We have to add something to the grammar of the types in order for
Oh,
the...
yes, sorry, yep. Okay. So the reason I've introduced this is because this will become important on Thursday when I introduce dependent types, because this will be the key to integrating dependent types with the linearity. But for now, I'm going to stick with the previous sort of more informal linear presentation to keep things simple. Okay. So what does this have to do with complexity control? So I've shown you basically a programming language, which in some sense is worse in that you can write fewer programs in it. But what do you get for doing this? So first I'm going to go through a quick kind of bit of history about what I'm not going to do. So one way we can proceed, so implicit complexity via linearity. So the key thing to notice is that if we are in a linear system with the beta reduction rule, then unlike the full simply type lambda calculus, this has the nice property that this term is always smaller than this term, because this x can only appear once in M, right? And if for affine, it can appear at most once. So every time we take a beta reduction step, the term gets smaller. So we don't even need the rest of the type system. As long as we have the property that every x only appears at most once, we automatically have a strongly normalizing system. Any way we do beta reduction, we're going to make the term smaller. It's a dead simple proof. And by smaller, I mean that there's one extra constructor here, the lambda's gone. This one's got one fewer constructor, term gets smaller. So any kind of strategy for beta reducing lambda terms is going to be directly proportional. Number of beta reduction steps is going to be directly the size of the term. This is a nice property. Of course, what that actually means is that you can't write very much in this system. And what we're really missing from programming is the ability to express any kind of useful data types. So one way of fixing this is to add for all, so for all types, so something like and use those to encode data types. So this one is possible to prove this. Booleans.
Why don't you just add the lines?
Well, I'll get on to why we don't, why just is a word we can't use here.
Sorry,
Yeah.
what I meant was, why don't you add the types directly?
Yeah, I'm going to.
Okay.
But first, I'm going to show the way I'm doing it. Yeah.
So a reason why a term can't have, like, I mean, a lambda term won't having like more than one x is the consequences of not duplicating thing, right?
Yes.
All right.
Yeah. So this is why we do not want to duplicate things. Yeah. But I should write down.
Did you mean to use two different types of arrows for bool?
Right.
You're using two different types of arrows for bools. So are we going to introduce another
Oh,
type of arrow?
no,
Or
that was a mistake.
okay, thanks.
I've got to write down. So we can add for alls and then try and do church encodings.
It's the other way around for the sizes. Run for the sizes.
No, I think
No,
you're
no.
counting steps. Right?
This is the size of this one is equal to the size of this one plus one.
Oh,
Yeah, size. So a fairly easy thing to do is to add these kind of non-recursive ones, if you like. So Booleans we could represent as this. So this is, you give it, for any type we want to kind of eliminate to, we give it the true and the false, and it gives us one of them. As long as we can discard things, this is okay. We could try and church encode linearly the natural numbers, but we're going to get stuck here because any implementation of this is going to want to duplicate this as many times as it needs to do it. So what has been investigated in sort of starting from the light linear logic of Girard is putting in modalities which allow restricted duplication. So some kind of bang going here. So if we allow the full linear logic bang, so this allows unrestricted duplication. So that means there's A goes to this, then we're going to get the full power of simply typed lambda calculus, or in this case, polymorphically typed lambda calculus, because we can just duplicate. This is full linear logic. So other systems are, we annotate with a, this is a P, that's a polynomial. So this is bounded linear logic. So this tells us basically how many times we can eliminate this. So we're going to be able to, how many times you can duplicate. So if we have P plus Q, we can get to, this is bounded linear logic. And an even nicer system is the soft linear logic of Lafont, where every bang, so if we have something which is a bang, then it can also it can be duplicated once into n things, but then that doesn't give us the right to duplicate again. This is called soft linear logic. Okay. And a kind of fairly amazing thing is if we take the linear logic at the start, add a bang, which has this as an admissible rule, which you can add to the system, and encode church numerals like this, then actually gets us a p-time system up to having to insert a few extra bangs in certain places. So the normalization process for this captures soundly completely p-time. However, for the purposes of connecting to dependent type theory, these church encodings are terrible. They're really bad. First, well, one big problem is that this is an impredicative quantifier, which doesn't play well with most of the parts of type theory that we like universes and things like that. The other problem is that trying to work out the induction principles for these is just a mess. There is a system by Aaron Stump called Cedille, where he takes this very, very seriously and actually manages to make something work. But what we want is just pure proper data types that we have constructors and eliminators for. Okay. So as I had said, why don't we just do that? Why don't we just add data types? So let's assume that, why not just add data types? So let's assume that we have a natural number type. So I'm just going to write down the rules. So we're going to be pretty linear here. So we're going to have a 0. That requires no resources. If we have an n, then we can make it a successor. And then so this is how we build some natural numbers. And then if we have a natural number, we can eliminate it. So we need something to do in the 0 case, something to do in the successor case, and the natural number. Okay, so this is an iterator for the natural numbers. So given an A for the base case, and given an MS, which given the A for the n, gives us the A for the n plus 1. And then given a natural number, it gets us an A. And notice that there's no context allowed for the MZ and the MS. For the MZ, there could be. But for the MS, then if we had a gamma in here, that would get duplicated over and over again, or have to be used over and over again for every successor in the natural number. So we can't do that if we want to avoid duplication. Yep. Microphone.
Would it be permissible to have context if it had that bang P
Yes.
modality?
If it had a bang that allowed arbitrary duplication, yeah, because we're going to have to duplicate this for as many times as this natural number n.
Right, but the bang P that said you can once duplicate it to whatever number you want, and if you have the number right there, you can.
This one.
The soft one,
the
yeah.
soft one. This is statically known.
Ah, okay.
But yes, that's a good thought. Oh yes, so one thing I think, if someone's interested in a research question, is there a way of expressing this soft linear logic as one of these semi-ring graded systems? So I think there is, but it would be an interesting thing to find out.
Yeah. So the reason why we are I'm talking about full linear logic.
Yep.
So in that, like I was thinking, like why it is because we have unbounded restriction, like unbounded duplication allows. So I was thinking like why it was different from simply type lambda calculus.
Yep.
And there is the answer I came up with that. So the bang allows you to like mention certain types that that allows duplication, and there are certain types that do not allow duplication, right?
Yeah. Yeah, so you clearly delineate the ones you're going to use multiple times in the bang. But if you have this unrestricted one, there is a systematic translation from simply type lambda calculus into linear lambda calculus with this bang that inserts them at the right places.
So that's not what I expected.
No?
Because I expected you. So I'd expect you to store some costs inside the data type, because
Yeah, I'm getting there.
you're getting there. Okay.
Right, yeah. I'm saying, right, okay, why not just add data types? And I claim this is the
okay.
just. This is what you would do.
Oh, so it's a silly just, yeah.
Yeah.
Okay.
Well, okay, right. So I've at least like not completely screwed things up by having a gamma in the step case, right? So that would be just transliterating them. So this is at least linear, so legitimately linear. However, we can write the following sequence of programs, which is definitely going to take us way above linear and polynomial time complexity. So the first kind of shifty thing we can do is write a duplication function. So how do we do that? Right, so I'm going to curry the iter thing, so I'm not going to mention the last one, pretend it's a function from that to A, just to make it easier. So iter, in the base case, we make a pair of 2 zeros. In the step case, we have, just going to use pattern matching, pretend that's a let. Right, so using the iterator, we can iterate over a natural number and generate 2 of them. So now, even though for arbitrary types we can't do duplication, for our natural numbers we can. We can also write add. And due to the restrictions on the context in the iterator, we have to be a little bit clever about this, but so in particular, we can't use any free variables in the 0 case and the successor case. We have to write this as iter lambda y for the 0 case, right? So we're going to iterate on the first one, producing a function of this type. So that's going to be this function here, which in the base case takes the second argument. In the step case, we've got our recursive call, which I'm going to call R. We've got our Y, and then we do the successor of R of Y. Okay, so that's addition expressed using this iterator. So now we've got the ability to duplicate numbers and the ability to add them. So now we can multiply. So in this case, right, okay, we're going to use, I'm going to make implicit use of affineness here to throw away the number when we multiply by 0. But you can in fact write a discard in the same way you write duck, just by returning star for every step. So here we take the second number and we return 0, because multiplying anything by 0 is 0. And here we have the recursor and the second argument. So what we're going to do, we're going to duplicate this argument. and then add it to the result and multiplying by the rest. All right, is that right? So now, just using this linear iterator, we can duplicate, we can add, we can multiply, and then we can exponentiate by doing this again. We can just repeat multiplication, duplicating the number every time. And as soon as we can construct a thing that we can iterate on, we can do something that takes that number of steps. This is, in fact, let me use technology. So we just have to change this and this. So this is now 1. And this is now vol. Right, so now just using this linear iterator, if we just added data types with an iteration construct, even though the iterator was linear, didn't actually apparently duplicate any resources, we can construct a exponentiation function. And then using this exponentiation function, we can just repeat something 2 to the n times or 3 to the n times for the size of the input. Okay. So I think I'm not going to finish everything I wanted to in the remaining time. But so how do we fix this? So we try and fix this by having a think about if we want to capture polynomial time, which is meant to be what feasible computation is, then what can we do? So let's think about what polynomial time does and why are complexity theorists interested in polynomial time. So it's sort of meant to be, oh, this is what makes this is what meant to represent feasible computation. And then you think, well, what about n to the 1,000? Why is that a feasible computation? But you can get to it by thinking just in terms of like how we compose things. So polynomial time is constructed so we should be able to iterate through the input, right? If the input is a size n, then we should be able to do at least n steps of thing, right? So that should be feasible. So polynomial time is feasible. So we should be able to iterate through the input. Assuming the input's a fixed thing. We should be able to compose feasible things. So if we have one feasible program and a second feasible program, putting them together should be feasible. So feasibility composes. And so this would only get us still to kind of linear time, right? So we can do something 3 or 5 or 16n, because we do n steps, and then we can add them together here. The last part of why something should be feasible is that we should be able to iterate every time we iterate through the input, we should be able to iterate again. So the iteration should nest. And this is what gets us to polynomials. This allows us, so every time we go through the input, we're allowed to use the input again and go through that. So iterations nest. And I think what makes it so bad is, right, so once you say, okay, I can nest twice, then I can nest 3 times, and then the degree of the polynomial gets bigger and bigger and bigger. So what's sort of really meant by this is the same way that natural language nests, right? But people stop listening after you're down to your sort of 5th or 6th if within your sentence, and you're still going with your sort of branching decision tree. So iterations nest, but when people say feasible, they mean at most n to the 3, right, or 2 maybe. But this is computer science, so we can't stop ourselves. Once we've got a system which duplicates itself, it just keeps going. So these iterations can nest arbitrarily. And so what we're going to do is control what the input is and how we iterate over it, and separate things which are the input from things which the program generates and then does things on. Because what we were allowed to do in the previous example was take the input, it's maybe this bit, and then use that not only to iterate over, but also to generate new things which we then iterated over. So what we're going to try and do is separate the input, which is something which is going to stay the same, from the things we generate, and then not be able to, we can generate things from the input, but not be able to iterate over the things we generate. And I think this is the basis of almost all of the implicit computational complexity systems for polynomial time. We separate the ability to iterate over the input from the ability to construct things. So in a word, we're going to use NIMBYism. We are going to ban construction. Of useful things. So what we're going to do is we're going to ban construction of that NAT type that we can iterate over. So we're going to separate these two. We're going to be able to construct natural numbers that we can do case analysis on, but no iteration. And we're going to allow iteration over numbers which come from the input. And this is what we're going to do to make a polynomial time system. And I think now I'm out of time, so I'll finish there. Thank you. Questions?
Yep. This is very minor. Can you go back to the definition of adds? The last thing should be add RY, no? Because we're not doing a church encoding.
No, so the we can't this definition, yeah?
In the lambda y successor of RY.
Yeah, so what we're doing is we can't call add because we don't know recursion. So this one is saying that if our first number is 0, then the answer is the second number, that's 0 plus the thing. And this one is saying if the first number is successor of something, then we R is like the there's a function which takes the second number and gives us the sum of the first number and second number, and then we add the successor onto that. So this is literally saying add 0, or 0 plus y equals y. 1 plus x plus y is equal to 1 plus.
Okay, thanks.
I mean, writing things with these raw iterators is a bit mind-bending.
So you said it's not going to be complete or polytime in the sense that there will exist polynomial time computations that are not expressible in this?
No, so there will be programs that if you just read them as lambda calculus terms would indeed run in polynomial time, but the type system will reject them. That's what I mean. So it's not that controversial a statement in that there are correct programs which were rejected by type checkers.
Okay.
That under a particular operational semantics would just so happen to work anyway.
So, but if we magically know that some basic building block is polynomial time, can we add it as like a built-in function to this and still maintain the guarantee?
Yeah.
Okay, thanks.
Yeah, when you were talking about one of the other ones, I think the soft linear logic, you said that it was silent and complete for free time.
Yes.
That means.
Oh, so what it means is anything you can write down in it, in that system, the original system that Yves Lefon showed was the cut elimination. There is a polynomial time cut elimination procedure, so it will normalize the proof in polynomial time. And also it's possible if, and we're going to start next time with this, the completeness results are if you have a Turing machine that you know, and you can encode the one step of that Turing machine as a function which doesn't iterate, and you know a polynomial, then you can construct a program which will iterate that one step, that polynomial number of times. So you can simulate a Turing machine which will execute in a polynomial number of steps in this system. And you can do it in soft linear logic as well. So that's how it works. So if you've got a problem that can be solved in polynomial time, then traditional thing is I have a Turing machine, which I know will complete within polynomial number of steps for the size of the input. Then you can encode that Turing machine into one of these languages. So you're not going to get a nice encoding, but it's nowhere.
So I think I probably know the answer to this, but can you add the additive connectives from linear logic to this just fine, or
Yes,
would that
yeah.
break something? No.
Yeah.
Can about the construction rules? Yeah, I mean the previous slide. Yeah, so in the construction rules for natural numbers, you don't need any resources to construct natural numbers, right?
No.
So that means, yeah, you can have arbitrary computation on the natural number, right?
Yeah. So that's another way of looking at the problem is that it didn't cost us anything to create natural numbers to iterate on. So the other way of doing it, which I'll show next time, is that you have to pay something to even to make zero.
Oh, yeah. Thanks.
Okay, let's not speak it again.
Okay, thank you.
Coffee.
Shall I just disconnect?